All right, let's see if we can get our area approximation a little bit better by using more rectangles. All right, in part D, let's repeat part A using 4 rectangles this time. Okay, and so part A, if you recall, let's go back up. We did the midpoint version, we did the right endpoint version. Part A is asking us to use left endpoint. Okay, so we're going to repeat with the left endpoint process. And again, I recommend that you get a little bit of a drawing going for yourself. I generated these with Desmos to help us out. So part A, for part D and part E, we're using left endpoint. Okay, so left endpoint. Okay, so same thing, but now if we have 4 rectangles, we want to realize that, oh, okay, if we're going all the way from 0 to 2, now what's the width of each of these? Okay, the width of each of these would be the 2 divided by 4. So that's 0.5 on the width for all of them, okay? All of those have a width of 0.5. Okay, so then if we want to do the area now, we're good to go. Make sure that as you're drawing each one of these rectangles, you make it so that you do left endpoints for each of them. So that first one would be there, and then I draw my rectangle straight across and down. And then another left endpoint, and straight across and down. Another left endpoint, straight across and down. And another left endpoint, straight across and down. Okay, so that's the way that you should get your rectangles ready. So the area, each one of these is just length times width, or width times height, however you want to think of it. So each of these is now 0.5 times the function value at the left endpoint. So the first one was the function value at 0 plus another length times width, 0.5 times the function value at, okay, so the next rectangle, the second one, has a function value at the corner right there at 0.5. Plus another width of 0.5 times the function value at 1, plus another 0.5 times the function value at, and that one is right there at 1.5. Okay. So something that's kind of nice about this, especially if you start using a lot of rectangles, notice that the width of all of them is supposed to be the same every single time. So this width of 0.5, that's there in every single spot. So we can actually simplify our calculations a little bit, even from the beginning, by having that 0.5 width factored out. Okay, because all of the widths are going to be the same. So in this sum of rectangles, that will be a GCF. So you can factor out that width, and then it's just going to be all of the different function values. So it simplifies your work a little bit, especially when we're dealing with, 4 or 8 or more rectangles. So you can kind of just skip right ahead to that moment as long as you know what the width is. Okay, so simplifies our work a little bit. So I'll just leave that 0.5 out there. And then f of 0, I'll write it out for now. We have 4 minus 0 squared plus 0.5. That's going to be 4 minus 0.5 squared plus 1 minus, or 4 minus 1 squared plus 4 minus 1.5 squared. Okay, and I'm just going to go ahead and use the calculator now to type all this in. So 0.5 times, okay, here we go. Square root of, okay, that's just 4, square root of 4, plus the square root of 4 minus 0.5 squared, plus the square root of 3, plus the square root of 4 minus 1.5 squared. Okay, and so I got 3.49. Okay, I'll go 5.7. Okay, and that is the answer for this one. And then we still want to think, how good of an estimate is this? Well, we're using left endpoint, and so this one, let's compare that answer to the first left endpoint we tried. The first left endpoint, we tried 3.7 something. This one's 3.49. So there's a little bit less of the extra on the outside, okay? A little bit less. So this is better than 2 rectangles from left endpoint. Okay, let's repeat it again using 8 rectangles. And again, this is left endpoint, because we're using part A, which said left endpoint. Okay, so if we have 8 rectangles, it's still this same distance of 2 all the way across. So we do need to know what is the width of each individual one. Okay, so the width of each is, okay, so it was 2 all the way across, and we want to divide by how many rectangles we're using. So 2 divided by 8, which is 1/4, or I'm going to write it as 0.25. Okay, the previous one, they were 0.5 width each time. This time the width is 0.25. Okay, we're still using left endpoints, and now I've got them all drawn there. Make sure that you do left endpoints for each one of those rectangles, and then draw them coming straight across. Okay, so we have to be a little bit careful here. It's not really all drawn perfectly because that's 0.25 is that function value. This is going to be 0.75 function value. Then there's the 1, then there's the 1.25 function value. Or not function, but these are the x values that we're going to need to plug into the function values. Okay, then there's the 1.5, then there's the 1.75. Those aren't the widths, those are just, I'm labeling so that I know how to plug in these different function values here. Okay, but the width on each one of these, all of those have the same width of 0.25 width. Okay, but I was just labeling my x-axis right there so that I could like think about what values I need to plug in for the height of each of these. Okay, so let's go ahead and do this. Like I said with the previous one, we know that the length times width, the width is the same every single time, so we can just go ahead and write that width already factored out. And then all we need to do is f of, and then each of the function values for the left endpoints. So the first rectangle was at 0. The height of the second rectangle was 0.25. Then we had 0.5. Then we had 0.75 and 1 and 1.25. 1.5. Okay, all of that. And so I'm not going to write down the next set of all of those with the square roots involved. I'm just going to go ahead and type it into my calculator. So bear with me for just a second. 0.25 times, okay, so this is going to be square root of 4 minus 0 squared plus square root of 4 minus 0.25 squared plus square root of 4 minus 0.5 squared plus square root of 4 minus 0.75 squared plus square root of 4 minus 1 squared plus square root of 4 minus 1.25 squared plus square root 4 minus 1.5 squared plus square root 4 minus 1.75 squared. And I'm really hoping I didn't make a syntax error on my calculator. Thank gosh, I got an answer out 3.33, okay, 98. So I'm gonna round this to, I'll just write it as 98. Okay, these are all being rounded, okay, but so that is the answer for the left endpoint method using 8 rectangles, okay? And so it's a little bit less than our previous one, okay? But it's still a slight bit of an overestimate because we can see this little bit poking out above the circle, okay? But it's getting better. Okay, and so maybe you already saw this down here, part F. Let's repeat part A using 100 rectangles. And I'm just kidding. Here's kind of a picture where I generated it with Desmos. And as you can see, if we did 100 rectangles, I'm definitely not going to do that. Okay, but just look at this right here. You can see that it's kind of like little fuzzy, kind of little rectangles kind of poking out of the sides here. But just notice that it's just really tightly fitting inside the circle. There's a little bit of extra sticking out of the sides, but not by much. So if we did 100 rectangles, it would be very close. So this number right here would be a little bit smaller, and there would be a lot less of this extra. And then it would be even better if we did 1,000 or 10,000 or 1,000,000,000, okay? And that's the concept of the limit, the method of exhaustion thing. So this process of approximating the area under a curve by using more and more rectangles can be generalized. So if we were using n rectangles, okay, like we were doing 2 and then 4 and then 8, to divide the interval from x equals 0 to x equals 2 into n equal parts, what we did is we can always find the difference from 2 minus 0, okay, divided by n, and that's what we did up here, 2 divided by n, okay, so 2 divided by 8. And we found out what the width was. And each rectangle has height corresponding to the function value at, and we were doing left endpoints, but you can do left, right, or midpoint of each rectangle. And then the more rectangles we use, the better the approximation of the true area. And I have a cool little link here for Desmos to explore this concept a little bit more, where we can actually plug in all kinds of different functions here. So you can play around with this a little bit. Right now, I have the same function that we were dealing with there, but I've got all of these different values that we can plug in where I want like the left endpoint and the right endpoint. So right now I have it set where we're going from 0 to 2. So I wouldn't touch those because unless you're doing a different function. But if we want to do the number of rectangles, you can slide it around here and do more and more and more rectangles. Okay, kind of cool where I can keep filling in all of the different rectangles. I can let n go all the way up to like 100, like in the previous picture, and you've got all these other rectangles there. And then down here, we can do like right endpoints if we wanted, or left endpoints, for example. So I can click on that box and I can turn on the left endpoints. And so we can see that the left endpoints with the different number of rectangles, you've got a lot of wasted extra space on the outside, but as we do more and more and more rectangles, that wasted space gets smaller and smaller and smaller and smaller, and we can see that you have less wasted space. And if we could imagine, let n go all the way to infinity, wouldn't you agree that that would be like a perfect approximation? Not even an approximation, a perfect amount for the area. Okay, you could also mess around. This is just fun. You could turn off the left endpoint one and do the right endpoint one. And then in the same way, we've got under approximations because these rectangles have that missing space. Okay, so this would be an under approximation. But if you let n keep going bigger and bigger and bigger, that missing space is shrinking and shrinking and shrinking and shrinking. And if you could imagine n goes all the way to infinity, then it would be exact. Okay, fun stuff. So yeah, play around with this. You can even change the function. Let's see, we can do midpoints as well, and it has the graph automatically happening for you. And so same thing, it doesn't even really matter if I did left, right, or middle endpoints. If we let the number of rectangles just go all the way as big as you could ever want, then it's going to be a perfect area. Okay. Really cool stuff. There's a trapezoid method there that I'm not going to get into. But you could also play around with this by changing the function. So if I wanted to change this function, you could try something else like, oh, I don't know, how about x squared, for example. And so now I can change, maybe I wanted to just do this from 1 to 3. Okay, and I only wanted to look at this region from 1 to 3. Now I can do like my left endpoints or my right endpoints, and we can play around with a different function with a different number of rectangles and get better and better and better approximations. If I zoom out a little bit, see this parabola here, we can get the area underneath this parabola between the x-axis and the parabola from 1 to 3. And the more rectangles we use, the more perfect that area is going to be approximated by. let n go to infinity, and we should, in theory, get a perfect area. Okay, so a lot of fun here to play around with this in Desmos. I invite you to use this. You can enter whatever function you want right there. Do your left endpoint and right endpoint, or your starting point and your finishing point, which can be adjusted to wherever you want that to go. Okay, and then you can check to do your left endpoint or your right endpoint, and you can mess around with the number of rectangles that you want to use. Okay. Something that's kind of interesting to point out is depending on the left end, it actually depends on the concavity of the function, whether or not left endpoints or right endpoints end up being an underestimate or an overestimate. So kind of interesting to think about. This parabola that we have right here is concave up. Notice that the right endpoints are giving you an overestimate. And if we do the left endpoints, that gives you an underestimate. So that's like the opposite of the circle one that we did, because the circle one that we did that's concave down through that region. Okay, and when we were doing those endpoints, where was it? 0 to 2. It's concave down through that region. And so that's why left endpoints end up being an overestimate, and then right endpoints end up being an underestimate. Okay, so the concavity of the graph determines which method ends up being an underestimate or an overestimate. Okay, lots of cool stuff to explore there. So I invite you to take a look at that Desmos page. Okay, so I did mention that this is actually the graph of a quarter of a circle. Note that the function f of x equals the square root of 4 minus x squared. We can write that as y equals. Okay, and then square both sides and get, and then we can add the x squared over. We end up with x squared plus y squared equals 4, which is the equation of a circle centered at the origin with radius 2. Okay, the region we have been considering is 1/4 of that circle. And so if we use the area formula that we already know about, area equals pi r squared, we can get the exact area as 1/4 of pi r squared, because it's a fourth of a circle. So 1/4 of pi times 4, that's just pi, which ends up being approximately 3.14159. You know the value of pi. So as we were doing these different approximations, notice we were a little bit too high. The exact area should be pi. 3.4, a little bit too big. 3.3, getting a little bit closer, but it should be about 3.14 something. So if we did the process with 100, it would probably be pretty close. But we know that it should be approaching this value. Okay, and so as the number of rectangles increases without bound, the sum of the areas of these rectangles gets closer and closer to the true area of the region. We can write this as the limit as n approaches infinity of the sum of areas of n rectangles directly equals pi for this example. Okay, awesome stuff. Kind of like doing calculus before we even knew what calculus was. Okay, now I'll make a new video to get into the definite integral. So stick around for that.